recording this. Right. 12:33. All right. All right. Let's check here. All right. So I'm going to jump into number 5. All right. So number 5 says, well, I would, and this is, let me do this. Be better. I get myself probably less confused if I group my tabs together. Okay. And so number 5, scroll up a little bit from this morning. Let's get started on that one. This one says a rectangular loop of area A is placed in a region where the magnetic field is perpendicular to the plane of the loop. All right, so maybe I will begin by saying, all right, I'm going to take a rectangular loop. Oh, okay, I'll do the loop. Okay, so here's a rectangular loop. And
I'm share your phone.
Oh, thank you. I was feeling like I forgot something. I was speeding along here. I forgot to share my screen. All right, so let's, I guess when I turned it on, it kind of made me mentally skip that. Nice. All right, so this is this is what I was doing. I was drawing a rectangular loop. All right, so I'll draw a rectangular loop, and then I think it said the region where the magnetic field is perpendicular to the plane. So, so I'm going to draw the plane in the piece of paper. So perpendicular to that would be maybe something like this. And maybe I'll just make it the field kind of spread out in a bigger space than the rectangle. Maybe I better keep reading because I think they implied that. A rectangular loop of area A is placed in a region where the magnetic field is perpendicular to the plane of the loop. The magnitude of the field is allowed to vary according to this equation. So I'll put in the equation. So B equals, okay, some maximum value, and then it looks like it decays with an exponential decay. So it starts with this maximum and then diminishes down exponentially, where B max and tau are constants. The field has a constant value of B max, for t less than 0. Okay, so if I'm plotting the magnetic field versus time, looks like we start off with some kind of large value, maximum value, and as soon as time hits 0, it begins to exponentially decay away. So we start with a B max. Okay, use Faraday's law to show that the induced EMF in the loop is given by this equation. All right, so as with all the problems of this chapter, and you guys heard me say that in the first session many, many times, but starting a new session here, I'm just going to emphasize this is the crutch of the chapter, which makes it, in some sense, a short chapter, but not an easy chapter. So it is really short. It is really about Faraday's law, and then the direction comes from Lenz's law. And so I'll just say here that, use Faraday's law. So this is Faraday's law. And so I'm going to calculate the change in flux in that rectangle. Now, n is the number of turns in the rectangle. And since they just say a rectangular loop, I'm going to come to the conclusion that they're talking about one wrapping around rectangle. Okay. They don't say what the material is made out of. So in other words, this could be a mathematical rectangle. and then this is the EMF, or it could be a legitimate material, and that could have been made out of, say, a metal, because then if you get an EMF with a metal, you'll get a current. It could have been made out of plastic, so then you would just get an EMF, but the resistance of plastic is so high that I would say, well, we just get an EMF, we don't really get any current. Although I guess you could say the resistance is just really big, so the current is really small. So even a piece of plastic shaped into a rectangle may give you some small amount of current. But either way, and probably because this is only number 5, we don't go as far as asking things that are a bit more advanced that we did in the last session, like what is the current, what is the force, what is the electric field, those kind of things. So I'm just going to solve this equation, but I wanted to emphasize what the N means. The N is the number of loops of that, whatever the area is where we're trying to see the EMF based upon the change of flux in that area. So there's the one. Then I have the time derivative, and it makes it look easy, the flux, when you just write it with a Greek letter, capital Phi with a sub B, but that's really a dot product between the magnetic field and the area vector. So we've got some vectors and we've got some integral to do, as well as a time derivative. So there's some tricky math in here, and that's, I think, what makes this concept kind of hard. And again, that's what I kept emphasizing last session, and I'm going to probably end up doing that all this session and the next session is this little integral here. All right, so I'm going to leave the time derivative alone for a moment, and I'm going to start then by taking the dot product. And the dot product, you take the magnitude of the field times the magnitude of the area times the cosine of the angle between them. So I'll start there with the angle between them, because back in the picture in the description, they were saying here that the plane is perpendicular to the field. Now, the normal vector is also perpendicular to the plane. And so the normal vector and the field are actually in the same direction. So that would be 0 degrees. I suppose it might be tempting to put 90 degrees, since the word perpendicular was actually used in the description of this problem. But what they are saying is perpendicular is the plane and the field. What this equation is saying is the angle between the area vector and the field. So just because they use the word perpendicular doesn't mean I would put 90 degrees here. In fact, that would be a mistake to put 90 degrees. The angle is actually 0 degrees. And of course, cosine of 0 is just 1. So the flux just goes, what we would say, straight through. There's no sliding angle or to it. So that's kind of the easy part. Now notice again, I've got some calculus. It's actually 2 pieces of calculus. One is the integral over the area, or within the area. The other is the time derivative. And if you look at the magnetic field, what they're saying is it has the same value everywhere in space, but changes with time. So I would describe this as a magnetic field that is constant in space, but varying with time. And the reason that's important here is because part of our calculus is an integral of space. And anything that's a constant in space can be pulled out of the integral. And B is a constant in space, but it is not a constant in time. So I want to be careful about kind of understanding how we're treating B. B has 2 pieces of calculus, and constants can be pulled out in front, but because one is an integral of space and the other is a derivative of time, we may be able to pull it in front of, say, the integral of space, which we did because it is a constant of space, but not pull it in front of the derivative with respect to time, because it's not a constant with time. And that's what we will see here. So I'm going to just pull the B here, but not all the way in front of the derivative of time. All right, so moving on from page 1 onto page 2, then I'm going to put an equal, and then I'll still have a derivative. Okay, and so here's B. But I'll actually do this integral. This then, once we pull the B out in front, just says add up all the little areas of that loop. So that would just be the area of that loop. And sometimes they give us length and width. Doesn't seem to give that. They just say it has area A, so I'll follow suit and just call that an A for area. Now, again, we've got two pieces here, and area doesn't change with time. This is a rectangle that doesn't change its dimension. An example number 24, where this was a metal rod that was sliding out on some rails, the rectangle kept getting bigger. There would be one where the area changed with time, but this one does not. So I'll put the area in front of the time derivative. And so I've got area in front, and I've got the time derivative of the field, and the field was B maximum times E to the minus T over the time constant. And so again, applying our calculus, B maximum by its definition is a constant, so we'll pull it out. Then we have a derivative of an exponential, and the derivative of an exponential here is the exponential within the chain rule. So that would be a minus 1 over tau. We take the derivative. Now, we probably should emphasize that Faraday's law is talking about a magnitude of it. So the fact that I have a negative here is kind of irrelevant, and so I'll just drop it. So the magnitude of the EMF is B times, or A times B maximum over the decay constant or time constant, and then E to the minus T over tau. In fact, a very common form of a decaying magnetic field is of this type. So I can see why the author picked this kind of early on in the problems and saying, hey, this would be a good example to do. The magnetic field decays away and follows an exponential. Depending on how it is set up and how it decays away would determine this time constant. But many of your magnetic fields, once they're turned off, decay away with this decay constant. Anyway, so that would be the EMF. And that does match A, so that's good. And then so B, it says, okay, now give us a numerical value if at 4 seconds, the area, I'm just going to put in some numbers here. So we've got a rectangle that has 0.16 square meters for the area. The maximum field, so it started at 0.35 Teslas. The decay constant is 2 seconds. So up here we would have e to the minus 4 over 2. That's e to the minus 2. So that's actually quite a bit of decay to time constants, because e the negative 2 is 14%. So this, it's when it first starts to decay, you get this value, and then multiply by how much the decay has risen. So we're down to 14% of what it was initially. And initially then would be 0.16 times 0.35 divided by 2. So it would be 0.028 initially, and then we'll multiply by that 13 to 14% number. And so 0.00379 volts is the magnitude of the EMF. And again, I'll say that, notice I...
One more time. So when you plugged in those numbers, you got 0.14, and then you multiplied, what was the original value?
What about 0.14?
Wait, so when you plugged in those numbers in your calculator, you got...
so this number, yeah, so this number I did that number first.
Oh, gotcha.
I probably confused you doing that, sorry.
Okay, so that whole value when you plug it into your calculator gives you that.
Right.
Okay, gotcha.
So 0.2028 for this number, which is the number I would get, and this is what I was kind of running through my head. This is what you would get when time is 0, because e to the 0 would be 1. So when this magnetic field first starts to decay, you would get this much voltage. And then it would decay away according to this factor. So we're down to 13 to 14% of it. And so taking that original value and then the 13 to 14% gives me what it would be 2 seconds later after the field started to drop.
Gotcha. Okay, thank you.
And like I said, very common. So this, I guess I would describe this as when your field was first turned off, you had an EMF that's, not real strong. It's only 28 thousandths of a volt, but it's measurable, noticeable. 2 seconds later, you're in the thousandths. And so those are kind of voltages that are pretty small and probably not, unless you're bothering to make and actually measure this, you don't really worry about. So when the field first shut off, you would have some issues. So if this was a computer, when you first shut it off, it can have an effect on other things in your processor. But 2 seconds later, nah, it's gone. In fact, you kind of see these electromagnetic pulses. I guess one of the places I've maybe seen those on security devices at stores where they want to keep something secure, maybe like a good set of headphones or earbuds. They have integrated in a little electronic loop that if you walk between those two plastic things on the exit doors, the beeper sets off because it resonates with it and then signals, hey, we have some induction, which is actually the next chapter. It's an application of Faraday's law. But to disable the security device, when you're at the cash register, they scan it and they put it on top of this, looks like a little plastic pad, but that pad has this big pulse that makes a strong field that decays away. And that field is so strong that you get a strong enough voltage initially that makes enough current in that little security loop that it fries the security loop. The security loop actually burns up. Now, not enough that you see smoke or you smell anything burning or you see flames, but it burns up that loop, and that loop is no good anymore. And so that way, when you walk in front of the security doors, it doesn't beep it. The loop has been fried. Anyway, so that's kind of how they do those. And I guess electromagnetic pulses in terms of terrorism is kind of a big thing too, that a large electromagnetic pulse would make these high voltages. And so like my laptop I'm using right now would experience it just because it's near this electromagnetic pulse. So somebody did something outside, I could feel that effect, a lightning strike, or I could do it naturally. Anyways, and that could have a tendency to get enough voltage to burn out some of the electronics in my laptop. And so now my laptop doesn't work just because of something that happened outside. Now, obviously, the further away I am, the less effect it has. So that's kind of the thing. So anyways, but I kind of digress into some of the usefulnesses of this whole idea. But that can be helpful when you kind of see the usefulness of this. You, I think, get a little more interested in it. And but I think this material can be pretty obvious why it's useful. And the way the author does a good job, like we did 3 chapters on electric fields and then applications of it, and then we did some magnetic fields and then some applications, and now we're doing induction, and the next chapter is actually a couple chapters are then applications of it. So we're going to see this in our circuitry and other fun things. All right, so I believe number 37 was the next one. I'll double check that. 1253. And let me just check the chat here. Yeah, 37. I don't know why my chat always goes back to a default I don't like. All right, so let's try another one here. Oh, you know what? Let me just check. I did promise 121 people they had priority, but I don't think I've seen any here around here today. No. Okay, okay. So let's go to number 37. So back down to where we were before the break. We did 33. Oh, and then 37 is the next one. All right. So 37 says that you have a long solenoid with its axis along the x-axis and consists of 200 turns per meter of wire that carries a steady current of 15 amps. All right. So let me kind of rudely draw this solenoid. So here's what I'll call, I guess, the core of the solenoid. And maybe I have a wire that comes up and goes over the top. So here's my solenoid. And so I've got a lot of wires. They say little n, this is what we call the turn density or loop density. They say is 200 loops in 1 meter. Okay. And then they have a steady current. And I don't really have any kind of indication of what direction the current is. So I'm just going to draw one on here and then see if I need to redraw it. But I'm just going to take it this way. What that, of course, would do then is make a magnetic field in the solenoid. And in my picture, would make a magnetic field. And according to Ampere's law, so according to, well, I guess it's Ampere's law, but the equation we got for a solenoid was mu naught times the turn density times the current. And so the solenoid was one that was part of chapter 30. It wasn't on your test. I kind of had to pick either a solenoid or a toroid, and you guys remember the toroid was on the test. But so far, I would say this has nothing to do with chapter 31. This has to do with chapter 30 and the magnetic field. Now, of course, 31 is the change in the flux, so it makes sense that we really got to understand chapter 30 before we can do 31, because 30 is where the magnetic field and hence the magnetic flux is coming from before we can have any change to it. So everything I've said so far is me kind of drawing a picture and an equation of chapter 30. So I'll call this old stuff, although it's only a week old. So I'm sure you're still kind of struggling with it and trying to remember all these equations. And but that's why I didn't derive this equation. I'm not going to do, unless somebody wants me to, and go back to Ampere's law and derive it for a solenoid. So what we learned in chapter 30 is this is the equation for a solenoid, and the solenoid has a uniform field. That was a really neat thing, that everywhere inside, this is the field inside, 0 on the outside of the solenoid, but it's very strong. It's this number on the inside, and it's uniform on the inside. And I think that's what I really needed to know. So this was kind of a first step, is kind of a review of chapter 30 and saying, okay, what do I know about a solenoid? Because then it goes on to say a coil is then formed with 30 turns of thin wire around a circular frame that has a radius of 8 centimeters. The coil is placed inside of the solenoid and mounted on an axis that is a diameter of the coil and coincides with the y-axis. Okay, so there's a lot of words there, maybe a change of color. One of the things I got in that is this coil that is going to be placed inside of this solenoid. So the solenoid must have an opening bigger than the coil so I can get it in, because they say that the coil has a diameter of 8 centimeters. So I'm going to draw in here a coil, and I'll do a few little windings around. I won't try to draw all 30 that they say, but I would say N is equal to 30. Now, one thing I noticed right away that I better make sure I don't confuse is what are the turns in the solenoid and what are the turns in the coil? Got to keep those straight. In fact, I don't even know how many turns are in the solenoid. I just know that there's 200 per meter. I don't know how long it is. A meter is pretty long, so it's probably not a meter long. You know, maybe it's only like a quarter of a meter long, 25 centimeters. At which point, there's really then only a quarter, which I guess would be 50 turns. So again, I don't really know how many, but that's fine because when we derived the equation for the field from a solenoid, it did not matter how many turns there was. It was a turn density. So I need the 200. I don't really need to know how many there are. So like I said, if it's a whole meter, I guess it would be 200. If it's half a meter, I guess it would only be 100. If there was a quarter of a meter, I guess it would only be 50. And a quarter of a meter seems like a good number to me. It's 25 centimeters. So, but in either case, the important one then is this N is actually the number of turns. It's not the turn density. It's actually how many are there. So I use a capital N and there's 30 of them. Okay. And the fact that they're thin makes me think that I can view this as a plane. And so this is kind of like a flat coin, if you will. Little nickel here. So this nickel is actually inside of this solenoid. So if my solenoid was this piece of paper here, then what they're saying is this coin is inside. So that's what I'm trying to draw here. I'm trying to draw this coin inside. Hey, stayed up. I didn't think it would. Okay. So then, as I continue to read this, it says, and I'll read it again. It says a coil is formed by wrapping 30 turns of thin wire around a circular frame that has a radius of 8 centimeters. Oh, the radius is 8. I think earlier on I might have said the diameter was 8. So this, but whatever I said, so the diameter of this is 16 centimeters. The radius is 8 centimeters. The coil is placed inside a solenoid and mounted on an axis that is the diameter of the coil, okay, and coincides with the y-axis. So looks like I'll just put the y-axis right here. So somehow this is mounted. Diameter of the coil corresponds with the y-axis. The coil is then rotated up with an angular speed of 4 pi radians per second. So it looks something like this. This little circular wire is rotating. That.
Would it make a difference the direction of rotation? Like if it's rotating top to bottom? Like north to south?
Well,
versus east to west?
I think it could. Let me think it through. I can think of where things that wouldn't matter. Let's see. If it's along a diameter, I guess no, because if it were to rotate this way, there would be a change of flux, just like this way. Now, if it rotated along an axis of symmetry, so it rotated like a wheel, like this, like that, then the flux goes this way, then there would be no change in flux. So yes, then it would make a difference. But it looks like as long as I'm rotating around any diameter, no, it wouldn't matter. Yeah. So actually that'll make it easier for me to spin too. I can just kind of spin it like that. Okay, so imagine it spinning there. Oops, now it stopped. But spinning like that. Okay. But the picture I'm trying to get you to see is there's some flux going from right to left. And when you switch the angle, you change the flux. So the flux depends on the area, the magnetic field, and the angle. And so if any one of those changes, there'll be a change in flux. And so this problem is different than any of the other problems we've done. We've had problems where the field is changing, or today. We've had a field changing. That's the one we just did, and it was also the one right before the break. And then the other two we did had area. Well, one of them, like 24, we definitely say the area was changing, but 25, I don't know if you, or 29, I don't know if you'd say the area is changing. It moved into the field and out of the field. So you might say more that the field was changing on that one. But anyways, what I am trying to say is this is the first one we've done together today where the flux changes because the angle changes. So that makes this one kind of uniquely special here. I think there's other ones that the angles change, but this is the first one I've come across with you guys today that has the flux changing due to the angle. Okay. But I am going to say this, as I say this with all the problems, is the EMF is equal to the number of turns of your coil and times the rate of change of the magnetic flux. So you're only going to get an EMF if there's a change in flux. And I'll say it again, that change in flux can come from the field changing, the area changing, or the angle changing. And in this case, the angle is changing. Now I better read the question here before I go too far. The plane of the coil is in a YZ axis, at time equals to 0. So if I do kind of the X, and I've got to put Y up, because remember they said it rotated around a Y axis, and the way I drew it in my picture, I've already chose my Y axis. And I'll choose then the X axis to be kind of the, well, I guess I shouldn't say I chose it. They said it at the beginning that they wanted the X axis to be the axis of the solenoid. And so that's the direction of the field. And so the Z axis would be coming out of the plane of the paper or screen, whatever word you want me to put there. And so what they're saying here is that the plane of the coil is in the YZ. So it's like this. When time equals to 0. Okay, so that just kind of tells me where it starts. Then it says, determine the EMF generated in the coil as a function of time. So this is where Faraday's law comes in. And Faraday's law, just starting conceptually, says you will get an EMF if there's any change in flux. In other words, is there any change in the strength of the field? Is there any change in the area? Is there any change in the angle? And if any one of those three, or maybe two of the three, or maybe all three of the three change, then the answer is yes, there is something changing and there's going to be an EMF. So this one has just the angle changing, not the area. It's a circle. As you spin it, its area doesn't change. It's still the same area. And the field is in a solenoid. So a solenoid doesn't change unless the current changes. But they said it was a steady current of 15. So the field isn't going to change, the area isn't going to change, but the angle is. So let's run through the calculations. So the first thing I would do is put down a 30 here for the number of turns in this coil. I'm trying to find the EMF in that coil. That's why the number of turns 30 is important, not the number of turns in the solenoid. And then it's the time derivative of, and now I have to do the flux. And so here's this B dot dA. And here's something, that we haven't done today. But when I say B dA cosine theta, I think all the problems we've done today, the angle did not change, and it was always 0 degrees between the magnetic field and the area vector. But now with this thing spinning, the area vector is changing its direction. And so the angle between them keeps changing. So with this thing spinning, this has got to be a function of time. Now, we can write it as a function of time if we want. Oh, actually, before I even do that, why don't I do this? Why don't I point out that B is a constant in space? That's from our chapter 30, that the magnetic field has this much everywhere inside the solenoid. So everywhere in this coil, the field has this strength. And since the current doesn't change with time, the field also doesn't change with time. So I could actually pull this factor of B not only in front of the integral, but also in front of the derivative. And so that's what makes this one a little different than some of the other ones we did. The other ones, the last two we did, the magnetic field changed with time. So we pulled it in front of the integral, but not in front of the time derivative. This one, we can pull it all the way in front. And then we just have an integral of dA. Now, you could also argue that this angle changes only with time, but not with space. Now, let's see if that made any sense. Let's take just a moment in time. Let's say time 0. Time 0, we said it looked like this. And if you were to look here sideways at every little piece of area that makes up this coil here, the area vector would be in the same direction. So at this moment, every little area vector on here would be 0 degrees. Now, a little bit later, and I'll just turn it and lay it flat, the angle would change. So I am saying that the angle changes with time. But let's take this quarter over rotation and notice then that the area vector now would be going down into the paper. And it would do that for every section of this plane in the coil. And so the angle would be 90 degrees between the magnetic field and the area vector for every little piece. So again, I would say that the area vector is a constant in space, but changes with time. And so every little section, if you can kind of look at this thing as little tiny pieces, the area vector of every little chunk is the same, and hence it is the same angle between the area vector and the magnetic field everywhere along this. That's a long way of saying that I could take this cosine of the angle that does change with time, but doesn't change with space in front of the integral. And then so what I have is the 30 turns the magnetic field. Here I have the derivative of cosine theta, okay? And that theta does change with time, so I don't want to pull it in front of the derivative with time. But what I am going to point out is then right here, I just have the integral of the area, which is that area of this circular loop. So that's just the area of a circle. And I could write that as pi r squared. And then more than that, pi r squared is something that doesn't change with time. So I could actually bring it in front of the derivative. So the only thing changing with time is the angle. So this is what I was saying earlier. The area doesn't change with time. The magnetic field doesn't change with time, but the angle does. So 30 times b pi r squared. And now if I take the derivative with respect to time of a cosine, let's see. So for a cosine, take its derivative, you get what? A negative sine theta, and then the chain rule. How does the angle change with time? We can debate on keeping that negative because we are talking about, one way positive and one way is negative. So not too worried about that negative, but I'll just keep it for the moment. And then I will put in what I do know. So this is the 30 turns. The magnetic field, this is where the chapter 30 that I got started with is. This is the magnetic field from the solenoid. So I'll put that in there. This is the pi r squared. This is the sine of the angle. And then this is the rate at which the angle is changing. Now, I guess at this point, I'll go to page 2 and say, well, now we need to go back to our mechanics and talk about rotational speeds and stuff. So this will take us all the way back to chapter 10 in Survey, and I think it's chapter 10 in the OpenStax also, where we're talking about a rotating object. Maybe one of the kinematic equations you remember is that the angle equals the initial angle plus the angular speed times time plus 1/2 and the angular acceleration times squared. That was an equation that talked about the angle of something rotated, but only if it had a constant acceleration. So this was kind of a limited discussion, but it often happens that way. So we had a lot of this discussion, and it's appropriate here because our angular acceleration is a constant. In fact, it's a good constant. It's an easy constant. It's 0. So this is saying our angle would be its starting angle times its angular speed multiplied by time, because this has no angular acceleration. don't know if this is what they want us to do, but we could say that, okay, in its starting position, which they said was the YZ plane right here, something like that, why don't we call that the initial angle of a 0? So calling this one 0 lets us reduce to something really simple. And so if we put that in here, we now have -30 mu naught Ni pi r squared. And we have sine omega t. And then we can take the derivative with respect to t, and then that's just its angular speed. So if we now put in our numbers, we get -30 mu naught, the permeability of free space, is 4 pi times 10 to the -7. The little n is what we talked about for the solenoid, the turn density, 200. The current is the 15 amps. The area of the coil, well, there's the pi, and I think I need to come back to the problem. Didn't I read 8 centimeters for the radius? Yeah, circular frame of radius 8 centimeters. So 0.08 squared for the radius. And if you'll go ahead, I'm going to go ahead and write the omega first. So the omega is the angular speed. So they say this is a 4 pi. And then we have a sine of 4 pi t. So here's a function of time. So when they say determine the EMF as a function of time, what they're saying here is put in everything else, everything you know, but of course you can't put for time. I didn't give you a specific time. And so you should have everything except for time in there. So this will ultimately be some number out in front, and then sine 4 pi t. And so all of this needs to be calculated. And like I said, the negative we could either add or drop. It really depends upon what you mean by the direction. That's why we put the absolute value. But using the sign, we'll know that the sign will go positive and then negative, positive and then negative. So the current's going to go clockwise and then counterclockwise and clockwise and counterclockwise. And as a side note, that was one of the things talked about in this chapter is how do we make most of the electricity here in our country, in the world for that matter, is we do something like this. We have a coil that is spinning in a constant magnetic field. And that spinning generates a voltage that does an alternating, or what we call AC voltage. And so if you don't know this already, it's definitely worth pointing out because we're now about to enter 3 chapters of applying this. And we're going to say, well, what's going on in our wall plug? You know, when I plug in that toaster, the electricity goes back and forth. It's alternating, and that's because the voltage alternates. And so we call this an AC voltage and an AC current for alternating current. And it's all because of the way we make our electricity. We don't make most of the electricity in this country with batteries. We make it with a spinning coil in a magnetic field. And now you just have to make something spin this. And so one example of making it spin would be just hooking it to a windmill. And so the wind blows and it spins this, making our electricity. Hydroelectric dams. This could hook to a paddle wheel, and the flowing of water through some pipes built inside the dam can spin this and generate it. So this is a really good example of a practical application of how our electricity is made around the world, most of it, which is why you need those little cubes that look like this to plug in your phone. You know, you got this little cube here, and so what you're doing is you're plugging this into the wall, which makes voltages back and forth, AC, and eventually through a little bit of electronics in here, comes out this end in a constant one direction. And that's how batteries are DC. Batteries are the simplest ones to talk about. That's why that's all we've talked about so far. We're just now getting to the point that, hey, we're ready to shift gears away from batteries and start talking about electricity that is generated from generators. So when I go to charge my phone, I got to switch the AC, which is made by something like this, into one directional, because that's what my battery needs to charge. And in fact, that's how my phone operates, because my phone runs off my battery. So the phone operates DC. Actually, same thing with my laptop here. Here's the plug for my laptop. So this goes to the wall. So what comes in here is an AC, but then it goes to my laptop. So it's got to convert it into DC, and that's what my laptop runs off of, and that's what my battery needs to charge it up. So right now, I've got this hooked into the wall, and it's converting it. In fact, it's kind of warm. Yeah, it's pretty warm, makes sense. And then it converts it, and the process of converting does make some heat. That's why it's warm. And then it makes a DC, which is going to my laptop. So I'm charging up my batteries right now. Although my goal is just to make sure it's plugged in so my battery doesn't die. I mean, my battery works great, but it wouldn't last all day on a Friday while we do these Zoom sessions. So got to have it plugged in. Anyways, so back to our numbers. We're going to get some kind of voltage with a sinusoidal pattern to it. That's why I got kind of sidetracked here. So let me put in some numbers here. So here's 30 times a 4 times a pi times a 1 times 10 to the negative 7 times a 200 times a 15 times another pi times a 0.08 squared times a 4 times another pi. And I think that's it. Ta-da. All right, so this is going to make 0.028, so not much of a voltage here. This isn't anything to brag about. Maybe I'll do one more significant figure. And there it is. So if I leave the negative sign here and plot the EMF as a function of time with the negative sign, I get it going like a negative sine function. And I suppose now you can see why the negative didn't matter. You know, this would just keep going on. And so where you call time equal to 0 is kind of your choice. So if you call time equal to 0 there, it becomes a positive sine function. If you call time equal to 0 here, it becomes a positive cosine function. If you call time equal to 0 here, you get a negative cosine function. And if you did it here, you would have some combination of sines and cosines. And so we can play all kinds of math tricks with this. And so this part really isn't that important, neither is that. This is what's important, is how high up or down does the voltage change from its maximum to its minimum, its maximum, minimum, that kind of thing here. All right, well, I hope I, again, didn't talk too much here. Let me check then the answer to number 37. They've got 28.6 millivolts fine, and they don't have a negative sign. So, nice. Haha, good. And let me come back. I don't think this one had a part A, B, C. I think that was it. 37. Determine the EMF generated by the coil as a function of time. Okay, good. That one was enough in itself. It didn't need a part A, B, C. In fact, you guys know that some of these have A, B, C. They're kind of long. You saw that, of course, on the test. They're just long problem. So we got to take the new stuff together with a bunch of old stuff. All right, so let's move to the next one here. All right, that was 37. So let's move on to 64.
Yeah.
Okay, awesome. And let me just write down the time, 1:28 already. Okay. Time flies when I'm talking. All right, put my little circle up here so I know where it is when I need it again here. Okay, so what I say, number 64. All right, so number 64. Nice. Over to that tab and scroll down. Oh, this, yeah, this. This is a nice picture. And you know what I want to do is I think I'm going to print this up so I can put it in the camera a little better. Because this has got a lot of detail, and I think it would be good to see. So let me copy it. Let's see. Can I paste it into the print? How about? Well, I'll just go Microsoft Word. That should work. And make it a little bigger. That matters. Let me just shoot this out the printer so I can draw on this one. I think I can do a better job with the color details of all of this. But because it's very three-dimensional and goes back and we're pulling on a weight, I think I should print it here. All right, so let me read the question also here. So here's the printout. But it says here that a bar of mass little m, so there's little m, and be careful because there is a capital. Okay, so a bar of mass little m. Oh, and I just noticed this is a magenta one. I bet. All right, I bet we're going to be here a while. Okay, so a bar of mass little m in figure 64 is pulled horizontally across a parallel frictionless rails by a massless string. So here's a string that's pulling on it, okay, that passes over a light and frictionless pulley that is attached to a suspended object of mass capital M. Okay, so this mass is going down. So capital MG is the force pulling this one down. And of course, there'd be some tension here. And that tension over here, T, is what pulls this bar across. And so this is a lot like the number 24 we did at the beginning of today, where then this rectangle here, which has a magnetic field, so that's what the B is, although I suppose I should keep reading here. It says a uniform magnetic field of magnitude B and a distance of little l, so right here, from the going back, little l, and the distance between the rails is L. The only significant electrical resistance is right here. There is the resistance. So R is shown connecting the rails at the end. Derive an expression that gives the speed. Now that's an interesting question in itself, because given its speed, this is going to sound like a lot of physics 121 stuff. We've got weight, we've got tension, but we also got this motion EMF, which is going to make a voltage and a current and a magnetic force. So it's definitely related to this chapter, but it's also related to a lot of mechanics stuff. All right, but there it is. Derive an expression that gives the horizontal speed of the bar as a function of time, assuming that the suspended object was released from rest. All right. Well, I'll tell you what, let me start with the stuff that's new for this chapter. But it's also the same that we did for problem number 24, and that is this loop. So let me do Faraday's law. Faraday's law says that the magnitude in the EMF is equal to the number of turns, the time derivative of the change in flux. Okay. Now, if you remember doing this, and we'll do it again, we got BLV for the magnitude of the EMF induced. So I'm going to try that again. Let's see. So I'm looking up here at this rectangle, noting that this weight pulls it down and makes the rectangle wider. I'm going to call this distance x. We already know going back into the three-dimensional view is the little l. So there's only one rectangular loop, so this capital N would be a 1. Then I would have the derivative of, and then I would have this b dot dA again. Now, taking this dot product, this would be b dA cosine of some angle. And again, like 24, and I think also 29, you make a plane here. The normal vector is perpendicular to plane, which would be up, but the magnetic field is up. So this angle is 0. And it's 0 everywhere. Everywhere in here, the plane is up, and everywhere in here, the magnetic field is up. And of course, cosine of 0 is 1. So the angle is 0 degrees everywhere on there. And notice that they said that the magnetic field is a constant. So I'm going to pull it in front. I think they meant not only is it a constant in space, but also in time. So this field does not change as you move over in space, but it also doesn't change in each moment in time. So not only could I move the b in front of this integral, I could move the b in front of the time derivative. Now, as far as the area of this rectangle, the area then would be the little l times the x. And the L, the length, doesn't change, but the X does. As this bar moves out, the X keeps getting bigger and bigger. So again, you can't have an EMF unless something is changing with time, whether it be the area or the field or the angle. So the last problem we did, the angle changed. This one, the area is changing. And in fact, this right here would be listed as the velocity. And so there it is, the same equation we derived in 24 and I think 29, and also back in the book, we call it a motion EMF. This is BLV. So this is the amount of voltage that is created in this loop. So that's the part, and I would even say the only part that is new to this problem, but we've got a lot of work to do. There's a lot of things to put together. So I'm going to refer to this as page 1 and then go on to page 2 here. Because if I were to say, well, sticking with this semester, but going back to chapter 27, I would say, is there any currents? And I'd say, well, yeah, because now that we just shown there was a voltage, so that's what's new to chapter 31, when I apply Ohm's law to it, which I guess is chapter 27, there would be then some current created in this loop, and the voltage is BLV. That's the voltage we get from this moving, which a motion EMF, this moving metal bar in a magnetic field. Sometimes we like to use the phrase moving magnets make electricity. But then the resistance is only this thing here. I guess they're saying the rest of it doesn't really have any much resistance, so we can ignore it. So I would just divide it by R. So that would be the magnitude of the current. Now, maybe I should put in red, like I did before, the direction of the current. So let's come back to this chapter and use Lenz's law here. So remember, Faraday law gives us the magnitude of the EMF, and Lenz's law gives us the direction. All right, so as this is moving out, we are getting in this rectangle more and more flux pointing upward. So that's an increase in upward flux. So the secondary flux, that is the flux created from the current, would be opposing that a change. So since more is trying to go up, we would create a flux, I'm going to use my thumb, down. And if I do the thumbs up symbol, with my thumb pointing down, I want my flux to be down, the currents would then go across and in. So current would go across, my fingers would go in. There's the current going in, and then left to right, and then over here, forward to back. Okay. Now, if we then take this current and apply, well, like we were doing in 29, the force is, well, the Lorentz force, the magnetic force, is I L cross B. We could look at the forces on each of the straight pieces of this rectangle. Now, to be quite honest, the only thing I really care about is the force on the one that's moving, because the question just says derive an expression for the horizontal speed of the bar. And this is kind of the crutch of the problem. You need to realize that there is a force other than the tension pulling on it. The tension pulling on it, which is related to this weight coming down, that's something that we did in mechanics. So I think you know that there is a tension pulling on this. But what is new is there would be a magnetic force to the right. Maybe I should have done that in red like I did in 24. Maybe I'll make it a big long arrow. So it'll be force sub B. See, and if you do this cross product, you would put your fingers in the direction of the current. I put my fingers in the direction of the current, which is into the paper, and then I close my fingers upward, because that's the direction of the magnetic field. My thumb is pointing to the right. So it's opposing it from moving, which again is what we saw in 24 and 29. We saw that the induced EMF made a current. The current then had a force because it was in a magnetic field. And the end result was that force always opposed the motion. So keeping those other two in mind doesn't surprise me that the force is opposite. In fact, I'd be very surprised had the force gone in the same direction as the tension, because that means it would just keep going faster and faster and faster, normal than a regular falling one. And you would have to ask yourself, then if it's going faster, where did it get all of a sudden this extra energy from? Whereas it's not a surprise that it opposes it, because then you would say, well, it doesn't have as much energy as it would have without a magnetic field. Where did that energy go? Well, because it made current and there's a resistor, it made heat right here. That's where the energy is. Okay. So, but if it was going the other way and you said it made electricity, which made heat, and it went faster, that would violate conservation of energy. That should be very bothersome. So you I'm glad it works out that way, and you should work it through. But to be quite honest, just thinking about the energy, we could have figured out that it has to oppose the motion. I mean, it's just got it. So opposing the flux also always ends up with opposing the motion. So that's kind of the shortcut. The real Lenz's law says it opposes the flux. The end result is it also opposes the motion. That's where it gets its energy from. So if you follow it through, you'll see that. So I did follow it through, and I do see that it opposes the motion. Okay, so again, focusing more on this semester before we go back to our mechanics, let me take, okay, I'll say it again, what I learned in this chapter right here. Here's the voltage. And then in chapter 27, here's the current. And in chapter 29, here is the Lorentz. And I will just maybe start with the angle and come back here. The current on this bar is going in, and the field's going straight up. That's 90 degrees. And that's, of course, why I did the little cross product thing, curving my fingers up 90 degrees, but my thumb is the direction. So I know the direction is that way, so let me not worry about direction. I'm just going to put the magnitude of the force. But the first thing I would do is to say that angle is 90 degrees. Okay. And sine of 90 is 1. The current, well, that's what we did up here. So this is a B, an L, a V over R. The L in this is the length of the wire, which again would be the length of this bar. And so the length of the bar is that little L. So the big L and the little r become one and the same for this problem. I think the number 29, the length of the current was the width of the coil. So the L became a W. Here's the B again. And so we get the B squared, the L squared, the V over the R for the magnitude of this magnetic force. In fact, I'm going to switch back to the paperwork. I can find it. We did before the break. I think this was the 29 or 33. Well, anyways, but here we said the magnetic force, we had that N squared, B squared. This was the length squared velocity. So I guess I'm going to say we see the same thing, except instead of having width, we have length, and instead of having N, we have just the number 1. Maybe I should have started there. By the way, I never know if I should start all the way back at fundamentals. I think I should, because I think that explains everything.
Yeah.
But for a test or for homework, I think you could start right here. And so all the last, it's like 18 minutes of talking, which got us here, you could have started because your author did this for you and you had done it in every problem. So feel free to start there. Here's the great thing about it. If you recognize it, you can start right there and the problem goes pretty quickly. If you don't recognize it, well, then you have to start from scratch and it takes you longer and you spend more time and you learn more because you didn't learn this the first time. So I like to think of these homework problems as kind of self-correcting. When you really understand the material, they go really quick. When you don't understand the material, they take a long time, but that's good. That's what you need. You need to spend a lot of time because you don't understand it.
Yeah.
So that's what I mean by it's self-correcting. Okay, so when I explain it from scratch, it takes a long time because I usually go all the way back here. All right, so I'll say it again. Starting from scratch, you'll get here in about 15 minutes, or you could have started there. Now, that's the part from this semester. Because what makes this, I think, a hard problem is you need to go back to your free body diagrams. I'm going to make 2 of them. One of them is the hanging mass, and the other one is the moving bar. So if I come back to the picture and I kind of do this free body diagram, I would say I have pulling down a force of capital mg and lifting up a tension. Now, if I do the free body diagram for the bar, in terms of left and right, I have the tension pulling it to the left, and then this is the new one, the magnetic force pulling it to the right. I guess technically I have a normal force where the bar is touching this rail, and I have a gravitational force pulling down on it, but this up and down motion, and well, there is no up and down motion, and these up and down forces actually are going to become irrelevant. So I'm going to just kind of mentally cross them out because I'm trying to figure out the velocity of this bar. So let me then, now that I have the free body diagram, go to step 3, which is to say, let me apply it to the moving bar. Okay.
Okay.
And kind of untraditional, let me call to the left the positive direction, just so that it's moving positive. And I'm also going to do that for the hanging mass. Let me just call down the positive x direction. So even though this is kind of unconventional, I kind of like it for this problem. That way both of these objects are moving in the positive x direction. And like I said, this one looks really weird because not only do I call down positive, but I call it x. But it's just kind of nice to have the x's of one body match the x's of the other, and the plus of one matching the plus of the other. And plus is easier for me. So if you'll allow me some freedom to kind of just mess with our conventional coordinate system, it just kind of makes the thought process a little bit easier because, again, splitting this in these two pieces, if I were to apply the math here and say, add up all the forces in the x direction, because that has to equal mass times the acceleration in the x direction, I could look at these forces and say it's tension that way, magnetic force the other way, and magnetic force would be in the negative direction. You know, that looks funny, okay, but the right is my negative direction. And then that has to equal to m times the acceleration in the x direction. Now, the reason that can be useful is because the acceleration does have velocity in it. And that is the point of this question. The question says, derive an expression for the speed. So I want to solve for this. So I need to solve a differential equation. Now, let me keep going, because what we said earlier here on page 2 is this is the equation for the magnetic force. It is B squared, L squared, V squared, there's the V, R equals M dV dt. So this is the part that I was saying about Physics 121. If I got the bar and I'm looking at the free body diagram for the bar, and I add up all the forces and set it equal to MA, and I put in the magnetic force, which is the stuff that's new for this semester, together with the acceleration as the derivative velocity, I have a wonderful equation that looks like it's going to be kind of hard to solve for velocity. But I do have an equation that has velocity in it. It's a differential equation, and I am going to solve it. And I still have a lot of work to do, even though I've been working on this for quite a while. I can solve that crazy thing. Okay.
Yeah.
Now, I will point out that the general rule is your answer should include numbers if they give you numbers, which this problem doesn't, or symbols if they give you symbols, but it should be the symbols they gave you. And if you look closely, they did not give me a symbol for tension. They gave me a symbol for a magnetic field, so that's fine to leave in there. They gave me a symbol for L, that's fine to leave there. Velocity is what I'm looking for. They gave me little m, they gave me capital R. So I've got no problem with leaving those in there, but I do have a problem with the tension. So I probably need to get rid of the tension, and that's where this other equation is going to come into play. So let's do the hanging. So again, calling down positive, and I'm just going to say, let's add up the forces in the x direction. That has to equal to ma. Now my x direction is down and positive is down. So this force is capital mg. The tension on this object is upward, which is its negative direction. And that has to equal the mass of this object, which is capital M, and the acceleration of this object, dv dt. Although, this is kind of nice, since they are hooked together with this string, the acceleration of this one going down and the bar going left are the same. So this, which is the velocity of the hanging weight, dv dt, and this velocity of the bar are actually one and the same. So that's kind of nice. But as you can see, I could then solve this for tension. So this would become mg minus m dv dt equals tension, and put it into here. And so let me do that. So this would become mg minus m dv dt minus b squared L squared v squared r squared equals little m dv. All right. Now, I think you can see why this was a magenta one. Because not only did I have to go all the way back to physics 121 and do my free body diagrams and add up my forces, I needed to realize that what they're looking for is something that doesn't have a t in it. So I needed the two equations to combine together to get rid of the t. Now I have one big equation that has